In a previous video, I established that the exponential function defined in the complex numbers is e to the z equals e to the x times parentheses cosine of y plus I sine of y. The complex logarithm is defined using the definition of the exponential function in the complex numbers. When I say the exponential function, I of course mean the exponential function in base e. So suppose we have the equation e to the w equals z. We need to solve for w to find the expression for the logarithm of base e, where the argument is z. So suppose w is a complex number in the form x plus iy, and suppose z is in the exponential form re to the I theta, where r is the absolute value of z and theta is the argument of z. The argument of a complex number is the angle between the positive real axis and the line segment from the origin to the point on the complex plane representing the complex number in the counterclockwise direction. If e to the w equals z, then w equals log of z. That's the foundational definition of a logarithm, and we are extending this to the complex numbers to derive a definition of the complex logarithm of base e. We would also need to use the complex definition of e to the w and assume w is a complex number. When I say log of z, I mean the logarithm of base e, where z is a complex number. I know this is confusing because in the real numbers, when we say log of z, we usually mean the common logarithm of base 10, but keep in mind that in this video, by log of z, I mean the logarithm of base e in the complex numbers. E to the w is also equal to e to the x plus iy, which equals e to the x times e to the iy, according to how we define the complex exponential. So if we plug in the expressions for e to the w and z, we get the equation e to the x times e to the iy equals re to the I theta. Both expressions are complex numbers in exponential form, so for the two to be equal, the absolute values and the arguments must both be the same. The absolute value of e to the x times e to the iy is e to the x, and the argument is y, so e to the x equals r, and y equals theta plus 2 pi k for all integer values of k. This is because a difference of any integer multiple of 2 pi in radians doesn't change the angle on the complex plane, since 2 pi represents a full circle in radians. So y just needs to equal theta, or theta plus any integer multiple of 2 pi, in order for the two angles to be equivalent on the complex plane. We can rewrite the first equation by taking the natural logarithm in the real numbers on both sides to get x equals ln of r. When I say ln of r, I mean the natural logarithm of base e defined in the real numbers, which is distinct from log of z. The reason we can do this is because both e to the x and the absolute value r are real numbers, so we can apply the ln function defined in the reals on both sides. So we took the natural logarithm of e to the x and the natural logarithm of r to get x equals ln of r, and y still equals theta plus 2 pi k for all integer values of k. R is just the absolute value of z, so x equals ln of the absolute value of z. Theta is the argument of z, but theta plus 2 pi k is also equivalent to theta on the complex plane, so y equals arg of z. Arg of z is the function representing the argument of a complex number, and yes, arg of z is a multi-valued function, which means it can take on multiple values. And in fact, it can take on infinitely many values because there are infinitely many ways to represent an angle on the complex plane, since we could add any integer multiple of 2 pi to represent the same angle with different numerical values. Since w equals log of z and w equals x plus iy, we can conclude that log of z equals ln of the absolute value of z plus I arg of z, and this comes from the expressions for x and y that we found in terms of z. So this means log of z in the complex numbers is also a multi-valued function because it contains arg of z, which itself is a multi-valued function. The reason that the complex logarithm is a multi-valued function is because the exponential function in the complex numbers is not injective, which means the function has multiple distinct values in the domain, which outputs the same value. This results in the complex logarithm having multiple outputs for a single input value in the domain. Also keep in mind that log of z is distinct from ln of z, as mentioned earlier, and the reason why we needed to make this distinction is because log of z is the natural logarithm in the complex numbers, which is multi-valued, while the ln function is single-valued. The exponential function in the complex numbers can also never equal 0, just like the exponential function in the reals. So the complex logarithm is also undefined for z equals 0. So the natural logarithm function in the complex numbers is defined for all non-zero complex numbers. So log of z is a multi-valued function, but there's another function, log of z, with a capital L, which represents the principal value of the logarithmic function. It's a way of restricting the output so that it becomes a single-valued function. Log of z, with a capital L, is defined as log of z equals ln of the absolute value of z plus I arg of z, where arg of z is written with a capital A. Arg of z with a capital A represents the principal argument of the complex number z, which is the unique argument of z that lies in the interval negative pi less than arg of z with a capital A less than or equal to pi. This ensures that the principal argument is a unique value. So log of z with a capital L equals ln of the absolute value of z plus I arg of z with a capital A, which is a single-valued function, since arg of z with a capital A is also single-valued. So another way to think about the argument function is to define arg of z in terms of the principal argument function, arg of z with a capital A. So arg of z with a capital A is the argument of the complex number z in between negative pi non-inclusive and pi inclusive. And arg of z is just the principal argument plus any integer multiple of 2 pi. If we apply the formula for the complex logarithm, log of negative 4 equals ln of the absolute value of negative 4 plus I arg of negative 4. Negative 4 is a negative real number, and if we plot negative 4 on the complex plane, it would lie on the negative real axis. So if we look at it graphically, we can clearly see that the principal argument of negative 4 is pi. So if we apply the formula for log of z, log of negative 4 equals ln of the absolute value of negative 4 plus I arg of negative 4. The absolute value of negative 4 is 4, and arg of negative 4 is just arg of negative 4 with a capital A plus any integer multiple of 2 pi. So the expression becomes ln of 4 plus I times arg of negative 4 plus 2 pi k for all integer values of k, and keep in mind, this is the principal argument function, arg of z, with a capital A. So since the principal argument of negative 4 is pi, as mentioned earlier, the expression is equal to ln of 4 plus parentheses pi plus 2 pi k times I for all integer values of k. So these are all the possible values for log of negative 4. If we want to find the principal value of log of negative 4, we simply drop the plus 2 pi k for all integer values and only use the principal argument for the imaginary part. So the principal value of log of negative 4, using the log function with the capital L, is ln of 4 plus pi I. So let's do an example of taking the natural logarithm of a complex number. So let's say we have log of 1 plus I. If we apply the formula, log of 1 plus I equals ln of the absolute value of 1 plus I arg of 1 plus I. We can also rewrite arg of I plus 1 as arg of I plus 1 with a capital A plus 2 pi k for all integer values of k, so the expression is in terms of the principal argument. If we look at the point 1 plus I on the complex plane, we can see that the principal argument of I plus 1 is pi over 4. If we want to calculate this, we can use the formula for the principal argument when the point is in the first quadrant, which is arg of x plus iy with a capital A is equal to arctan of y over x. So using this formula, we can see that arg of 1 plus I equals arctan of 1 over 1, which equals pi over 4. The absolute value of 1 plus I is the square root of 2 if we use the formula for the absolute value of a complex number. So if we plug in these values, the expression is equivalent to ln of the square root of 2 plus parentheses pi over 4 plus 2 pi k times I for all integer values of k. If we want to find the principal value of log of 1 plus I, we just need to drop the 2 pi k term, so log of 1 plus I with a capital L is just equal to ln of the square root of 2 plus pi over 4I.